Hello and welcome to our final presentation on object relations in 3D instance segmentation. 3D instance segmentation has as an input an RGB point cloud, and the output is a semantic prediction and an instance prediction for every point of that point cloud. Let me give you a quick motivation to our approach. If you see this little square here, guessing what this is supposed to be is very hard. But once we put it in context, it's not hard at all. This is why we propose to use a network to learn spatial relationships between instances to improve the semantic prediction. The input is a 3D point cloud, and we propose to use point group as a backbone network, as point group is the best scoring network on the ScanNet benchmark, which has code publicly available. The point group network outputs an instance prediction and a semantic prediction, but we only use the instance prediction, and we use semantic scores from point group instead of their semantic prediction. You can see our network that we propose back here, and the input to our network is a sequence of the class scores of an instance and the k nearest neighbor instances sorted by the distance to the instance. And then we want to update the semantic predictions with our network. We propose to use a transformer network for this task. The transformer network was originally designed for natural language processing tasks, but in natural language processing, there's also a spatial relationship between different words in a sentence, and we propose to use this for our spatial relationships in the 3D scene.
Now to some results. First of all, let me introduce our metric. So we use the predicted instances from point group, and as the ground truth labels of the instance, we use the majority vote of the ground truth labels of the points of this instance. Point group itself performed with an accuracy of 91.4%, which we took as an average of the accuracies per class, to not depend on unevenly distributed classes in our data set. We found out that we can train a model which increases the score to 93.3%, which is a decrease in error rates of over 20%. We also wanted to find out if our network really uses spatial relationships, and we did this with training one transformer network, which we only inputted one instance and the ground truth label, so no neighbors. For this setup, our network only performed 72.5%, had an accuracy of 72.5%, which greatly decreased. So we can conclude that we actually use the spatial relationship. In this scene, you can see how our network actually worked. First of all, one example where a table which was originally misclassified as other furniture was classified correctly as a table by our network. The second kind of reclassifications where we can see here, where an instance which was obviously originally a table was partly classified as other furniture, and our network reclassified it as a table correctly. For our future work, we want to feed in the new classifications from our network back into the clustering algorithm, because this way we can improve the instance scores for the cases where the instance was cluttered, and we can actually increase the prediction of the instance shape itself. We also want to take into consideration small instances which the point group network threw away, to try to reevaluate the score in them and recluster them as well. Finally, we want to test our improvements on the ScanNet benchmark. To wrap it up, I've already talked about the future work by an example of some visuals. And our contributions were we trained a network that was originally designed for natural language processing to perform spatial relationship on 3D scenes. And we were actually able to improve the score of the point group network from 91 to 93%, which is a reduction of error rate by 20%. This wraps up our small talk, and thanks for listening.